What do I know about radiation?
Actually, you probably already know more than you think. Simply put, radiation is the release of energy. Many kinds of radiation are familiar to us, as radio and TV signals, heat, visible light, and ultraviolet.
But when most people hear the word radiation, they think of other things. Things like atomic energy and radioactivity. The energy in this kind of radiation can cause changes in atoms, creating electrically charged atoms, which we call ions. Radiation which produces ions is called ionizing radiation. The aurora borealis, for example, is a visible effect of ionizing radiation, interacting with atoms in the upper atmosphere. All life has evolved in an environment filled with radiation. But unlike heat and light, it is invisible to our senses. We can't feel, see, hear, taste, or smell it. Before 1895, we didn't even know it existed. But though it's invisible to us, we can detect it by other means. Instruments such as Geiger counters allow us to detect and measure radiation. They can also produce an audible sound, which varies with the intensity of the radiation. We can better understand the forces at work in ionizing radiation if we enter the tiny world of the atom. Atoms are so small that a single human hair is 1,000,000 times thicker. But small as they are, atoms are made of even smaller units. These units have positive or negative charges, or no charge at all. At the center of this simple helium atom, we find a nucleus, made up of 2 protons and 2 neutrons. Orbiting this nucleus are 2 electrons. In this heavier atom of carbon, the nucleus contains 6 protons and 6 neutrons, and 6 electrons are orbiting the nucleus. This balance of charges, equal in strength, is what holds atoms together. This portrayal of atoms is only a representation, since the real sizes and distances involved are too varied to be accurately shown. The number of protons in the nucleus is the key to what kind of element the atom is. Everything in our world, and the universe beyond, is made up of atoms. Atoms which make up a family of more than 90 different elements. Each element is unique, with a specific number of protons. All the atoms of a given element will have the same number of protons, but the number of neutrons can vary. Such atoms are called isotopes. Uranium, as one example, has several isotopes.
Some atoms release energy by ejecting particles from their nuclei in the form of alpha, beta, or gamma radiation. Alpha radiation cannot penetrate substances very easily. It is stopped by something as simple as a single sheet of paper. Beta radiation is more penetrating, but it too is easily absorbed by a thicker material, such as a book. Gamma radiation passes right through most substances. To reduce its intensity, we must use even thicker and denser materials, such as concrete or lead. Atoms which emit this radiation are called radioactive isotopes, or radioisotopes. Radioisotopes are unstable atoms. They release radiation until they finally become stable and therefore non-radioactive. This process is called radioactive decay. We use the term half-life as a measure of the time it takes for an atom to decay. With some radioisotopes, this decay happens quickly, while in others, it can take a very long time.
We receive small amounts of radiation from uranium and other elements which are found everywhere on the planet, in rocks and soil. As they decay, some of these elements produce another radioactive element in the form of a gas, called radon. We can absorb radon decay products by breathing. We also receive cosmic radiation from our own sun and from the stars and galaxies. All of us have very small amounts of natural radioisotopes in our own bodies. We absorb these substances from the foods we eat and drink, and from the air we breathe. The sum of all this natural radiation is called background radiation. It accounts for about 80% of the radiation which an average Canadian receives in a lifetime. The other 20% comes from artificial sources.
Well, what are these artificial sources of radiation?
The production of radiation by artificial means had its beginning in 1895, when a German scientist discovered X-rays. Soon after, many radioactive elements were identified. Scientists devised theories to explain the structure of atoms and the forces at work inside them. Putting these theories to work, they discovered ways to control and exploit these forces, using devices such as reactors. In 1942, a milestone was reached when the first nuclear reactor went into service. Only 5 years later, Canadian scientists started up one of the first reactors in Canada, at Chalk River, Ontario. Nuclear fission, the process of splitting an atom, was a reality. This process creates tremendous amounts of energy in the form of heat and ionizing radiation. With the means to produce radiation artificially, scientists inherited a responsibility to control its use and to understand its effects.
Those first pioneers of radiation knew little about the harm it could cause, but they soon realized that ionizing radiation could have damaging effects upon living organisms. New research was devoted to finding answers and ways to protect people. The evolution of these studies gave rise to new sciences, such as health physics. Health physicists are concerned primarily with radiation protection, as applied to human populations. To accomplish this task, we needed a measurement process. Using a unit of dose measurement called a millisievert, we are able to measure the biological effects of energy absorbed from radiation.
Over the course of a year, the average Canadian will receive a little over 2 millisieverts of radiation from all natural sources. The natural dose can vary from person to person, since altitude and geography are factors. At higher elevations, people receive a bit more cosmic radiation. Because the atmosphere is thinner, more radiation gets through. Similarly, in some areas on our planet, rocks and soil contain more natural radioactive elements than elsewhere. People in such areas will receive a higher dose of so-called terrestrial radiation.
But what are the actual effects of radiation?
When ionizing radiation penetrates living tissues, the electrically charged atoms, or ions, can change the chemical structure of living cells. If enough radiation is absorbed, cells may be altered or destroyed. Living tissue has a great ability to repair itself, but in some cases, these cellular changes can develop into cancer. They could also cause genetic defects or visible skin effects. This brings into question how much radiation will cause serious harm. Exposure to a lethal amount would be a most unusual and unlikely situation. even exposure to moderate levels occurs only under the rarest of circumstances. When we examine low exposure levels of radiation, it's more difficult to predict the effects. In any given population, we know that some people will get cancer or pass on genetic defects. This is a normal process in the natural order of life. Exposure to sunlight, air pollution, toxic chemicals, smoking, viruses, and so forth may contribute to the incidence. But since we also know that radiation can cause these abnormalities, to be on the safe side, we must assume that there is some risk involved, even in low doses. However, it is impossible to say with any certainty that exposure to low levels of radiation will actually cause a disease or defect. There are simply too many other possibilities to say exactly which one is responsible. In the case of a radiation dose from an artificial source, such as an X-ray machine, the risk is balanced by the procedure's benefit to our health. If we look at a chest X-ray, the overall body dose is relatively small, about 7/100ths of a millisievert. We can compare this to a typical dose received from a natural source, such as an airplane flight. Because planes usually fly at high altitudes, the passengers will receive slightly more cosmic radiation than people on the ground. With this comparison, our chest X-ray equals approximately one return airplane flight from coast to coast in Canada. It's also about twice the dose you would receive from a large Canadian nuclear power station if you lived for a year at the plant gate.
If there is a risk, what's being done to protect us?
Natural sources of radiation do not present any appreciable risk to people or the environment. In recent years, there has been some concern over the level of natural radon gas in homes. While there's nothing to indicate household radon causes health problems, we can test for it and reduce the concentration if it's above normal. The vast majority of Canadians will mainly have contact with artificial radiation through routine medical and dental X-rays. Those people who work in radiation areas such as uranium mines, reactors, or nuclear medicine use three primary means to protect themselves from sources of radiation: shielding, time, and distance. People working with or near these sources are protected by barriers, which include things such as protective clothing and shielding of lead, concrete, and other heavy materials. When possible, they must also reduce the time that they spend near radiation sources. They can also dramatically reduce the amount of exposure by increasing the distance from radiation sources. People who work in these areas routinely wear devices called dosimeters. These devices are sensitive to ionizing radiation. They monitor and record cumulative doses. This universal symbol warns us when protection is needed. It appears wherever there is a potential for exposure to radiation. This includes work areas, waste and storage facilities, and all packages and shipments which contain radioactive materials.
If radiation carries certain risks, then why do we use it at all?
The answer to that, like many other potentially harmful things in our modern society, is that we have found many positive uses for radiation. It would be hard to imagine a modern dentist's office or a hospital without X-ray machines. Radiology, the science of X-rays and other penetrating radiation, allows doctors to see inside the human body. Both X-rays and radioisotopes are used for many diagnostic procedures. And just as radiation can cause cancer, it can also be used to cure it. Radiation is also used for sterilizing, in medicine and in other fields. Many countries whose economies depend upon food exports use radiation to eliminate bacteria which cause food to spoil. Radioisotopes are used in a number of consumer products, such as smoke detectors and emergency light sources. For security, we use X-rays at airports to inspect baggage. Various industries also use radiation to inspect structural welds in pipelines and in shipbuilding. Radiation is used as a valuable tool for scientific research. Radioisotopes play an important role in archaeology and in agriculture. Investigation into the complex world of physics is one of the purposes of nuclear reactors, like the one at Chalk River Laboratories. Similar reactors and particle accelerators are used to create radioisotopes, used in medicine and industry. The primary use of nuclear reactors is to generate electrical power. Large amounts of shielding and massive containment structures are some of the means that provide protection against radiation hazards.
But isn't the public exposed to radiation risks through nuclear waste and the transportation of nuclear materials?
These are definite public concerns, and there are very strict rules and regulations in the nuclear industry. The radiation risks from transportation are really only significant once a reactor is involved. So reactor byproducts and highly radioactive spent fuel are transported in extremely strong containers, which can withstand tremendous impacts in the event of an accident in transit. Overall, there are several 100,000 containers of radioactive materials transported in Canada each year for electricity production, medicine, science, and industry. All containers, large or small, must have adequate shielding to protect the people who handle them. They are also designed to withstand rough handling. The result is that accidents rarely cause the release of radiation. As for wastes, regularly inspected on-site storage is designed to minimize any effect upon the environment and to protect people. Power plants, for instance, store their most radioactive waste in engineered facilities such as water-filled pools and massive concrete canisters. Other licensed facilities store or dispose of the small amounts generated by industry and medicine.
But how can we be sure of what's going on in our communities?
There are a number of agencies who observe and record what is happening in our environment. They function to protect us and the environment against any misuse or hazard associated with radiation in the nuclear industry. These organizations carry out environmental monitoring programs. These programs measure levels of radioactivity in the air, drinking water, surface water, soil, and food. These programs also detect any radiation which might result from atmospheric weapons testing or nuclear accidents in other countries. Environmental monitoring provides important data on the presence and levels of radioactivity. Evaluating trends and making predictions, we are able to use these data to make responsible decisions about the use of radiation.
When we use radiation, we do so with the care and respect it deserves. And we know that when it's used properly, we need not fear it.
We've been using it since 1895, And with each new discovery, our knowledge continues to grow.